Now we proceed to the review of statistics. So before we talk about probability theory and its studies, the random variable, the properties of random variable, if we know the parameters of its distribution. But for statistics, the question studied here is a bit different. So for statistics, we don't know the parameter of a random variable or of some population. Okay? So what we do is to infer the parameters from the sample from our observations. So here, the first concept is a population, which can be any well-defined group of subjects. And the sum of their characteristics is described by some probability distribution. But you are not sure about the value of the parameter of that distribution. So we want to estimate or do hypothesis test from the data that we collected from the population. Okay? So the parameters are the we primarily study in the statistics. So let's think of a more specific example. For example, you want to know the average wage of workers, all the workers in the factory. Okay, so in this case, uh, the population is the workers in all the workers in the factory, and the parameter that we are interested in is the average wage of all the workers. So suppose there are 10,000 workers in a factory. It's very costly to ask their wage one by one. So what we do is do a random sampling. We randomly get, say, 100 workers from these 10,000 workers and record their wage. So this forms a random sample of wages from the population. So typically we require that the sampling procedure is random. Okay? So you don't follow a specific rule to to determine which worker you should ask about his or her wage. You randomly pick a worker and ask about her wage, and then randomly pick another worker. Okay? So by this way, you can get a random sample. Otherwise, the sample is not random. It will undermine the power of statistics. And again, we typically require that this for each observation in the sample are independently and identically distributed. Right? This idea notations here. Okay? And they are also we assume that they comes from the same distribution, and the parameter that we want to estimate, typically the unknown parameter, we denote it by theta. Okay, so for example, the theta is the average wage of all workers in the factory. Okay. So so how can we form a rational guess of the average wage, the parameter of that we are interested in? Okay? So basically, for example, if we are interested in the average wage of all the workers in the factory, and we have a random sample of 100 workers, okay, and we take the sample average of their wage. So we have See here, so x1 is the wage of worker 1, and x2 is the wage of worker 2 up to xn, the wage of worker 100. Right? And the x bar, the sample average, is simply equal to 1 over 100 x1 plus x2 plus x100. So uh, you sum the wage of all workers in your sample. In your sample, you have 100 workers, and divided by 100, you get the sample average of the wages of all workers. And we use this as a guess or estimator estimate of the population mean. Okay? Population mean, which means the average work the average wage of all workers in the factory, okay? Not in the sample. So that's so the sample average is estimate of the population mean. Okay, so here an estimator is a function of the sample, okay, in general. In general, maybe we're also interested in the variance of wage, so we can have a sample variance to estimate population variance. So estimator is a function. Okay? But the estimate is the actual outcome of an estimator. So by the way, because each sample, each observation is randomly drawn from the distribution, so it itself is a random variable. Right? So an estimator is a function of random variable. So it is also a random variable. So it also has a distribution, and the distribution of an estimator is called a sampling distribution. So if an estimator is also a random variable and it also has distribution, then it also has, for example, expectations and variance. Okay, so we call an estimator is unbiased if its expectation equal to the parameter that we are interested in, that we want to estimate. So, for example, if we use sample average to estimate the population mean, then the expectation of the sample average is this one, right? It equal because we have learned the property of expectations. We can take this 1 over n out of the bracket and take out the summation out of the bracket. Okay, so equal to 1 over n times the summation of the expectation of xi, because this xi follows the distribution, which has a mean mu of x, right? So here it equals to n over 1 So first, for each I, think of the example of that we have mentioned 100 worker. Okay, in your sample you have 100 worker, and each worker from the distribution fx mu of x is our parameter that we are interested in. We want to estimate. Okay? And the expectation of xi equal to mu of x. Right? Therefore, uh, this one equal to 1 over n is 100, for example. Okay, right? And we have shown that each e of xi equal to mu of x. So this is further equal to sum of n mu of x. So equal to n of mu of x divided by n, which equal to mu of x. Right. So the population, the sample mean here is an unbiased estimator of the population mean. Okay? And to estimate the population variance, the sample variance, okay, the unbiased estimator is s squared equal to 1 over n minus 1 times summation of xi minus x bar squared. So I miss squared here. So this is the unbiased estimator for the population variance. So in the Coursera MOOC, it will explain why here should we use n minus 1 instead of n. But let's just leave it for you. Okay. Uh, the other thing I want to mention is so suppose two estimators are both unbiased. Okay, W1 and W2. So for example, we use both x1 and x2 to estimate the sample, the population mean. Okay? But we say that x1 is efficient relative to, sorry, we say W1 is efficient relative to W2 if the variance of W1 is less than the variance of W2. As we have mentioned, this W1 and W2, these estimators, they are random variables per se, right? So they also have expectations and variance. If its a variance is smaller, then it's more efficient. Okay? Because if the variance is smaller, then we are kind of more confident about our estimates. Okay, so just remember this concept. The other concept I want to emphasize is about the large sample properties. So it basically tells you what could happen if the sample size is increasing. And we are particularly interested in the so-called consistent estimate. We want an estimate has the property which is called consistency, okay? Which basically means that if the sample size is growing, the estimate is becoming more precise about the parameter that we want to estimate. Okay, so the notation is a bit complicated. It basically means that if sample size n grows, then the estimator say w1, okay, w uh, becomes more precise or becomes or gets closer to theta, okay, gets closer to theta, the parameter that we want to estimate. Okay. Yeah. The notation here is a bit complicated. I guess maybe I should use more, not to get it too deep in this part. Okay, just have this concept. Uh, Another large sample property is called asymptotic normality. Okay? This is a very and it is related to the so-called central limit theorem, which is very powerful. Okay? So suppose we have a sequence of random variables. Okay, an example of this sequence random variables is suppose you have uh, a sequence of a sequence of random sample. In the first sample, you just have one observation. In the second sample, you have two observations, and in the third sample, you have three observations, for example. And for each sample, you have say sample average, right? And the sample average associated to each sample form a sequence of random variables. And now the question is, if the sample size is growing, what will for each sample, the sample average as an estimate for the population average is a random variable, right? So what if the sample size is growing, what will happen to the distribution of the estimator? Okay? So here it basically says that if we have a appropriate transformation of the estimator, okay, then as the sample size is growing, we will have the the estimator or the statistics converge to a normal distribution. But it requires basically two things. Okay, it requires that first of all, okay, it's not here, but the concept is when the sample size is growing, not here. The asymptotic normality concept states that as the sample size grows larger, the distribution of the sequence of the estimators or other random variables converge converges to a standard normal distribution. Okay, basically means that the distribution is kind of very similar to a standard normal distribution. Okay, sometimes we wrote this notation Zn is asymptotically follows the standard normal distribution. Okay. And I said this concept is closely related to the central limit theorem, which is very powerful. So, so suppose we have a random sample of size n, okay? And this x is drawn from population with mean mu and variance sigma squared. And now you have the sample average x bar n and denote the sample size here, okay? Which equal to the summation of x divided by n, right? So as I said, if n equal to 1, you have a sample with one observation, and the sample average is x1. If you have a sample size of if you have a sample with two observations, x1 and x2, then the sample average will be x1 plus x2 divided by 2, right? For example. And then we do a little bit transformation. Let x n bar minus mu divided by sigma square divided by square root of n. Okay? If we do this transformation, we get a new random variable Zn, right? And this Zn has the asymptotic normality property. Okay? It is asymptotically normally distributed. Okay? This is the central limit theorem. Okay? So the usefulness of the central limit theorem tells you if the sample size is large enough, most of the random variable can be considered, okay, or most of the statistics that we obtained from the random sample can be considered as normally distributed. This is very useful. Okay? And there are several general approach to do parameter estimations. Okay? So you may ask, how do the estimators come from? There are basically three major methods, but I don't want to go to the detail. Basically, I will talk about the idea. The first one is called method of moment. So the method of moment is simply replacing the population moments with sample moments. Okay? So for example, we use sample average to estimate population mean, because the sample average is the first moment for the sample, and population mean at the first moment for the population. Right? So we use basically the sample analogous to estimate the population moment. Okay? To match the population moment, then to obtain the estimate. The other way is called the maximum likelihood method. Okay, the maximum likelihood method is somehow, if even we so uh, suppose we know the parameter theta, right? Then we can specify the probability of observing a certain sample. Okay, so how can we estimate the theta? Basically, we choose the theta that maximize our probability to observing the data. Okay, this is the maximum likelihood method. The last thing is called least square method. Okay? So least square method basically tells you there is some so in the sample there is some measure of the moment that is closely matched to the parameter that we want to estimate. Okay? So what we do is basically subtract subtract them and get squared and then minimize the sum of the squared. So this is a bit abstract by far, and we will see that particularly in our class, we use the method called ordinary least square. It's basically a specific example of this square method. So actually, use sample average to estimate population mean is also a least square estimator. Okay. So so from here, if we have this xi minus m, okay, squared, and suppose we want to choose m to minimize this sum of squared, it will be we will obtain sample average. Okay. Anyway, so in general, there are basically three ways to do parameter estimations. Okay. So before we just talk about point estimation. Okay, we try to form a specific value to estimate the population parameter. Okay? But sometimes, do point estimation is not so precise. Okay, so and it does not provide any information about how likely our estimate is kind of correct. Right? So we would sometimes use so-called interval estimation or confidence interval to provide more information about our estimation of the population parameter. Okay, so I will not dig too deep in this topic by far. Okay, later when we talk about specific application in the regressions, okay, I will talk more. But here, you can think of this problem. How can we say, for example, if we have some unknown parameter, how can we construct interval so that you have 95% confidence. So there is a 95% likelihood that the true parameter is lying in this interval. Okay, the confidence interval basically answers this question. And the final topic related to statistics is this so-called hypothesis test. Okay? The hypothesis test, let me just briefly talk about the ideas. And I will ask you to refer to the Coursera MOOC to study more. Okay? So the hypothesis testing um, says that basically we have some initial guess about the parameter value. Okay? But now, say for example, we have, so you want to know the average wage of all workers in a factory. Okay, and your guess is that the average wage is say $1,000. But now you want to know how much likely that your guess is correct or not. So what we do is we're collecting data, right? We're collecting evidence. We obtain a random sample of 100 workers and ask about their wage and get the sample average. Now you have the sample average, and how much can you see, or what's what the sample average, okay, from this 100 worker sample, you get an average wage, say 115. Okay. Now you ask yourself how much you can see, or what's the probability that your initial guess that the average wage is 100 is correct. Okay. And if it's very likely to be correct, or sorry, so if it's very unlikely to be correct, say uh, the probability that your initial guess is correct is less than say 5% or 1%, then you reject the null hypothesis. You reject your initial assumption, okay, and accept uh, additional, or we call alternative hypothesis. Say the average wage is higher than 100. So this is basically the idea of hypothesis test. So my example here is a bit abstract, but it illustrates the ideas. But maybe you want to go through the notes, but all these things is also contained in the Coursera MOOC. So I don't want to spend too much time on this, and I will ask you to watch the Coursera MOOC video, okay, so that you basically have this idea, okay, basically learn the concept of hypothesis test. It's more important later we apply these things in the regressions. Okay. When we go to that step, I will develop more on both confidence interval and hypothesis test. Okay, that's it for my part in the statistics. Again, you still need to watch the Coursera MOOC video to complete your preparation in probability theory and statistics.